Okay, folks, during last night's online lesson, we came across the Nagel Point. It's on page 37 in your book, or the notes that I've sent you. Remember, we're working from Posamentia's book, and this is page 37, problem 2. So what I want to do is I want to discuss this proof with you in detail. The constructions that we needed to do and the things we needed to think about. So let's start and let's look at how this proof works. Okay, so the Nagel point problem says the following. If a point P is situated, point P here, is situated on the line segment BC, such that AB plus BP is equal to AC plus PC. Now it doesn't look that way because these lines look different in length. But that's the condition. That's the condition that they gave us, and this is what's important. Let me choose another color here. I'm going to use a lighter one. This is what is important as looking at the conditions of what this theorem says. So first of all, the conditions under which, the conditions under which we're going to operate when we try and prove this theorem. Okay, point Q is on the line segment AC, and the condition they give us for point Q is that BC plus CQ is equal to AB plus AQ. So it means if you add that distance to that distance, it's the same as that distance plus this distance. So, which means it's half of the perimeter of this triangle. Okay, but we're going to talk about that just now. And the same thing with the point R. Point R there has the condition that CB or BC plus BR is equal to AC plus AR. So again, that distance around the triangle is equal to this distance around the triangle. So what we should read about this is in the conditions there's equal distances that are indicated, and it uses the sides of the triangle ABC, the side plus a portion, this side plus a portion. Then that, this side plus a portion and that side plus a portion. So it uses the sides of the triangle and it works with equal distances. Now, having said that, let me just lock our focus. Having said that, folks, we need to also be aware of the theorems that we have in our arsenal so far. And in this chapter, the theorem is the Nagel point and Ceva's rule. Ceva. Okay, so we have those and whatever else we know that we can draw on. Now remember, Ceva works with nicely and proves concurrency nicely. So what we had to do for this particular problem is construct our E-circles. Now remember, we looked at that in last night's online lesson. Just for those of you that couldn't make it, you produce this side, you produce this side, and then you put a point on this line, and wherever point P is going to hit, you're going to find now, you find this angle bisector. So you choose that vertex, this point, tell Sketchpad to construct the angle bisector, it will construct this line. And you do the same for that point, and where those two lines cross, you find, so you'll select that vertex, this vertex, and a random point that you place on the line here. Okay? So I've chosen that point, this vertex, instructed to construct the angle bisector, and now I have this point over here. Then to construct each of these E-circles, you need to find out the distance. Now remember, these lines are all tangent. So you can construct a perpendicular to any perpendicular to that tangent line. Find the point where it intersects, select this point, select that point, and tell it to construct the circle by point and point here, center and point. Okay, so that will then show you the 3 points where these lines intersect with the 3 tangents. So you highlight this line, you highlight the circle, tell it to find the point where it intersects. It will then go onto the point there. Same here, highlight this line and highlight the circle. Tell computer to find intersection, it will construct that point, and the same then, highlight BC and you'll find B. So, those are angle bisectors. Now, the beauty about angle bisectors is the following. Let me get another color pen out of my bag here. The beauty is that it creates tangents. This little tangent there comes from point C and this tangent. So, that line is equal to this line. Now, the same for BP and this little part over here. And then, obviously, the same for A to there and A to this point here. So let's make this one 3 lines long, and then this one we're just going to indicate with a cross, that line equal to this one with a dot. So we know that all those, oh sorry, and I forgot one here. So let's make it a circle with a line through is equal to the circle with a line through there. Now I'm going to name those points now because I need them. Let's name this first point here M1, or just M, that tangency point, and this point N. Now, we must find what is significant about that. Okay, so let's first tell whoever's going to read our work what we are doing. We will be construct E circles, or you can also call them X circles, and let's name them what? Circle, what should we call this one? Let's call it circle 2, circle 1, and circle 3. So E circle C1, C2, and C3. Okay, so we construct them and let the points of tangency, so where these E circles touch with the triangle, with triangle ABC, be points P, Q, and R, like it is in the question. So all I'm doing is I'm saying I'm going to construct these E circles by producing those sides, construct this angle bisector, blah blah blah, and then I am saying the points where the E circles will touch will be point P, Q, R, so that it mimics what's in this triangle over here. Okay, so now what are we required to prove? We are required to prove that the line segments AP, CR, and BQ are concurrent. In other words, they cut in the same point here, and that point is what we call the Nagel point. Okay, so let's see what happens over here. The tangency point that lies opposite point A on BC is P. Okay? So that's the tangency point, and our diagram indicates that quite clearly. The points M and N lie on the sides AB produced and AC produced. So let's start with that. Points M and N lie on the sides, what is it, AB for M and AC produced. Okay, and what are they? They are tangents. Okay, so what, and therefore AM and AN are tangents. Okay, so there we go. AM here and AN are tangents to E or X circle C1. That is by construction, or by constructing the E circles. Okay, so what do we know? Therefore, AM will equal AN. They are tangents to circle C1 from point A. Okay, they're tangents from the same external point. But now we can say, but, what do we know? We know that MB or BM is equal to BP. How do we know that? For the same reason. Tangents to the circle C1 from the external point B. Okay, so we know that this little BM is equal to BP. So what is AM made of is what we should ask ourselves then. AM is usually, so by also, let's say also, AM is equal to AB, the side of the triangle AB, plus that extra length BM, which will mean it's now equal to AB plus BP. AM. Now by the same token, AN is equal to AC plus CN, which then makes it equal to AC, the side of the triangle, plus this portion CP. Okay, and that's for the same reason that the tangents from the point C to the E circle are equal to each other. So we've got those two expressions that we can draw on so long. Okay, now similarly, we can prove, we can argue the following. We can argue that AK, which is indeed, where's AK? K, let's put K over here. Now, the tangency points to that circle C2. I'm going to make K and L. And let's say the tangency points to C3 is ST. Okay, so that AK is equal to AR. And we also know that, where am I now? That BL here is equal to BR over there. Okay, and BL is equal to BR. And both of these are tangents from external point to C2. Different external points. Okay, so we know that those are equal to each other. So if we now talk about our tangents, CA plus CK, so CA is the one tangent, CK is the tangent in full. So CK is equal to CL, tangents to the circle C2 from point C. Okay, and the same thing happens. CK is equal to CA plus AK, which becomes CA plus AR at the end of the day. Okay, so we've got to realize that we don't have to prove it again. We want to get to the same conclusion as what we had here, that the line segment AM was equal to AB plus BP, and AN was AC plus CP. That is what we wanted. So we want the same here, that CK, the line CK is CA plus AR, and the tangent CL is equal to CB plus BR. Okay, that is our second important point that we wanted to get to. Now eventually we're going to see that AB plus BC will then be equal because those two tangents are equal. And the same here, that AC plus AR is equal to that one because these two tangents are equal to each other. Okay, and we're going to use that extensively. So similarly we've seen that, and also we're just going to go for the third one, that BA or BS is equal to BA plus AQ. BA plus AQ because why? AS is equal to AQ, and also that BC or BT is equal to BC plus CQ. So all of that we have found to be true, okay, in our proof. So we've seen that BT is equal to BS. So they didn't have to give us those conditions. They could have asked us to prove it, by the way, to prove that that plus that is equal to this plus that. And that is how we go about proving those things. Okay, so now since we have the fact that these things are equal, AB plus BP is equal to AC plus CP, either from this tangent work we did here, or from the fact that this was given. Okay, so we've got these things now. BC plus CQ is also equal to BA plus AQ, this component over there. And that AC plus AR, AC plus AR is equal to CB plus BR. Now folks, I'm breaking this up into two parts for you. So if you wanted to prove that component, you wanted to prove all of this relies on the fact that you're working with tangents. Okay, and tangents from the same point to each of these E circles. Brilliant proof here. And in this case, this was given. So what did they say? They said AB plus BP is equal to AC plus BC. Okay, so together, these things form the semi-perimeters. So if this part is equal to that part, then this journey is just as long as that journey, which means it's equal to a semi-perimeter of this particular triangle. Okay, so we're going to say let P be the semi-perimeter of triangle ABC. Now, if we let, as it's always a convention, that what lies opposite angle A is this side A. What lies opposite angle B is side B. And what lies opposite angle C is side C. Okay, so wherever we see those happening in here, we're going to change it to these numbers, and then obviously the semi-perimeter. So what does it mean? It means to us the following, that from this being the semi-perimeter, let me stick to black there, that P is equal to A plus B plus C divided by 2. The three sides halved. Okay. The distance basically halved. So what is AB? So now we can say, what is AB? AB is C. So C plus BP is equal to P, the semi-perimeter. If you go C plus BP, you've gone halfway through the perimeter. So what is BP? BP is equal to P minus C. The same on that side. AC is B. So B here plus that portion CP is P. Now you'll see I'm working with the portions as variables, okay, or as unknowns. I don't know how big that portion is. I do know how long that side is. It is labeled C. So CP will be P minus B. Now we go through all those sides and we do that. BC here, BC is A plus CQ is equal to P. So what is CQ? CQ is P minus A. This side AB, AB is equal to the size, small side C, is equal to AQ, or C plus rather, AQ is equal to the semi-perimeter, so AQ is equal to P minus C. Now folks, you might be asking me, why am I looking for these portions over here? Why am I looking for them? Because I'm going to use Ceva's theorem. Ceva's theorem says if that product of those proportions equals 1, then these lines are all concurrent. Okay, so we're going to do the third one. That's how we're going to use Ceva. This is small b plus AR is the semi-perimeter, so AR is the semi-perimeter minus B, and there small a plus BR. How did I know it's small a? Well, it's side CB and opposite to lies vertex A is equal to the semi-perimeter, so BR is equal to P minus A, and the same for that. How did I know that this is C? Because that was AB, and opposite AB lies the vertex C, so the length of AB is C. So these are the ones that I wanted, and this is what we're going to look for now. So now, finally now, we're going to say what is AR over RB, AR over BR multiplied by BP over PC multiplied by CQ over AQ. That's what we're looking at. And if that is 1, Ceva will help us out. AR is P minus B. BR over here is P minus A. BP is P minus C. PC is P minus B. Now already we can see those two are going to cancel. We multiplied with CQ, which is P minus A. Those two cancel. Over AQ, and AQ is P minus C. Now let's go bit for bit. There's a P minus A. I'm multiplying it with that. P minus C cancels. P minus B, P minus B. And we say thank you, Ceva. So by Ceva's theorem, we've now shown that AP and CR and AP, oh not AP, I've used BQ, are concurrent. That means they cut in this point here, and that is what we refer to as the Nagel point. So let me lift that last argument there. So it's quite a long proof, but you can see the proof relies on one advanced theorem and quite a few. This is logic, more or less. Okay, that is logic. So if we could have gone from there, we could have gone straight for the semi-perimeter and set this up. This here is just sort of proving that these relationships are indeed true, which we didn't have to do. The reason why I'm including them here is because this could have been broken up into two parts. We could have asked to show that AP plus BP is equal to AC plus CP. There's your proof. Okay? And then from that information, we work on towards the relationships with the perimeter. We use Ceva, and we see that they are indeed concurrent. Okay, folks, I hope that helped you to see that these things are not that complicated. You have to get used to using the advanced or the new theorems that you're learning to prove theorems that you could prove differently. But this one here is a good example of how these things merge with one another. Okay, now go and try the others.